Hello and welcome back to the course on statistics, and today we're talking about the Central Limit Theorem intuition. So we've already discussed what the Central Limit Theorem is all about, that whatever distribution you have in your population, the sampling distribution of your sample means will be normal, or will be close to normal, given that you take a lot of samples. The more samples you have and the larger those samples, the closer it will be to a normal distribution. But the point still stands that you will have a normal distribution regardless of what the underlying distribution of the population is. So let's have a look at how exactly this can come to be. Let's have a look at the intuitive side of things. So let's start with our distribution, the very unknown, very strange looking distribution here. And we'll just point out where the mean of this distribution is. And by looking at a picture, we can assess that it's somewhere over there, probably. Next, we're going to take a sample from here, and we're going to take a sample of 10 random elements from this distribution, and that's what it might look like. Because it's random, it could look anything, like anything that would come from this distribution, and therefore that's one of the examples. Now let's take another sample, and this is what this sample of 10 elements might look like. Let's take another sample. This one might look like that, and let's take another one. We've got that, and let's have a look at another one. There we go. So we've taken 5 so far. Of course, we need to take way more than that. We take lots and lots of samples. The more, the better. And then what happens is we find the mean. So we're going through the process of creating the sampling distribution. We've talked about it a couple of times, but now we're actually going through the process of creating the sampling distribution. So to create a sampling distribution, we need to find the sample means, or the mean of every single sample. So there's our mean of the first sample. There's our mean of the second sample, somewhere there. There's our mean of the third sample. It's more to the left because you can see there's more elements that came from the left side of the original distribution. There's our sample mean for the fourth sample, and there's our mean for the fifth sample. Is very far on the right because we don't have anything on the left, and so on. So we do that for the rest of them that we've picked out. And what we want to do next is we want to finally plot this sampling distribution of the sample mean. Next, what we want to do is take all of these sample means that we've found and project them onto our new chart. And that's what it'll look like. So here we only have 5 so far. And of course, we'll have way more because of all of those other steps that we're going to take in here, all of those other samples that we're going to look at. But even just 5 already starts to paint the picture. You can see that this is kind of the intuition behind things. So we're going to be understanding why is it going to be a normal distribution. So what we expect is a normal distribution, and there's going to be a couple of other things that we'll notice just now. So first of all, why would it be a normal distribution? Well, you can see that sometimes you kind of like get a sample from far away from here, from the left. Sometimes you get a sample from the right. But generally speaking, because you're sampling randomly from this distribution, it's kind of weighing towards the center. So even though there's it's a bimodal distribution, you've got a left hump and the right hump, they kind of balance each other out. So sometimes you get some values from here, which will be balanced out by values from here. So you get these values, which are balanced out by these. So this x is still close to the center. These values are balanced out by these values. This x is close to the center. Then this time, these values didn't really balance this one out. You got an x that is not exactly close to the center. It's going to be towards the tail of the distribution. Then again, you got an x that is balanced out. And then you got an x that is not balanced out. And the natural question that comes in here is, what if you only had one hump? You had the hump here. What if you didn't have this hump? Well, then this x wouldn't be here in the first place. This x is always going to be in the middle. Or is going to be at the mean. So that's why it would have been here. And then the whole thing would happen exactly the same way, but around a different mean. And that's the kind of like the magic to it, that the positioning of this x is the mean, and therefore it's kind of like in between, in the very center of this distribution, regardless of what it looks like. And therefore, when you're sampling, your new means are always going to be somewhere around the center. And moreover, you'll have more of them as you're closer to the center. As you get further away, it's going to happen rarer, because it's a more rare event to just get parts of the or just get elements from this distribution just from here. Given that if this is the mean, then there's an equal amount. Pretty much, there's an equal probability of getting some from here as well. So things like this are going to be quite rare, whereas this is going to be more common. And so once you take more of these samples, you will get something like that, which is a sampling distribution of the sample mean. And now the key here is that, or an additional insight, which we've already talked through, is that the mean of this sampling distribution is actually going to match up with this mean. So they're going to be exactly the same. And that's a very powerful, an additional powerful feature of the central limit theorem, because by constructing this sampling distribution, now you can just look at the mean of this sampling distribution and you will know the mean in your underlying population, because you don't actually know it from the start. You don't know this mean, but because you now know this sampling distribution and you know its mean, you will know the mean of the population. So that's a very powerful thing. So, or if you knew this, for some reason you knew this, then you can establish what the mean of the sampling distribution is. It's very powerful that they're linked together. So basically, if you put that into a sentence, then the mean of the sampling distribution of the sample mean is equal to the mean of the original distribution of the population. So as you can see, that sentence starting to grow and grow with lots of terms. But nevertheless, it is quite an intuitive concept when you think about it the way we thought about it. So let's write that down. Sampling distribution, the mu of x bar equals to mu. So a very important thing to note here is that, well, first of all, x bar that's x bar every single time, and therefore that's the sampling distribution. But remember at the start we said we will have a different notation for samples. For samples, we're not going to use mu, we're going to use x bar. So that's the sample notation. So the question is, why are we using mu here again for the sampling distribution? Why are not we using x bar of x bar or a different x bar? We are not treating this as a sample? Why are we treating it as a population? Well, that is because this is a different thing. It's not a sample. So these are samples, but this is not a sample. It's not necessarily a population, or this is the population, but at the same time, this is not a sample. And that's why we're going to be using the original characters or Greek letters. So we're going to be using mu for the sample mean, for the sampling distribution. That's number one. So we already know two things about the central limit theorem. First of all, that this is going to be a normal distribution no matter what. Second is that your mean of your sampling distribution of the sample mean is going to be equal to the mean of the original population. And the third thing about the central limit theorem, there has to be three, of course, is that the standard deviation of your sampling distribution is actually very linked, directly linked to your standard deviation of your original population. So the standard deviation of your sampling distribution is basically your standard deviation of your original population divided by square root of the number of observations that you're taking every time. So here would be a square root of 10. And that's a very important thing as well. So what it's basically saying, we're not going to prove it here because you would need to go into math for that. But what it's saying is that the more you take every single time, so if I wasn't taking, instead of 10, we were taking 100 observations for every sample, then your normal distribution here would be much narrower. Because remember, the standard deviation is a metric of variance, of how the values here vary. And if your n is greater, then this value will be lower. So your standard deviation will be lower, and therefore this will be much taller and narrower, meaning that your actual results here, your sample means will be very close to the mean of this distribution. So that's what this means, and it's kind of probably intuitive that the more you take, the more accurate, in like floating quotations, the more accurate is every single sample. So there we go. That's our central limit theorem, and three main elements to it: that this is a normal distribution, that the mean of your sampling distribution of your sampling mean is equal to the mean of the original population, that the standard deviation of your sampling distribution of the sample mean is linked to the standard deviation of the original population with that formula. Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.